So let's start over this slide before. Liquid chromatography, I remind you, because the mobile phase is liquid. If the mobile phase is a gas chromatography, it's a screen. The mobile phase is supercritical fluid, it's a supercritical fluid chromatography, and it's another kind of chromatography. Liquid chromatography, divided into packing material or non-packing material. Packing material is the main part of liquid chromatography, or and non-packing material, that's countercurrent chromatography that goes in two ways, hydrostatic or hydrodynamic countercurrent chromatography. This does not need to be explained more, stand by itself, and I don't know if we will have to use this naming or not. I'm presenting this considering chromatography covers all chromatographic system with a liquid stationary phase without packing any packing. So this is countercurrent chromatography covering all of those. Since countercurrent chromatography is chromatography, and we have a strong agreement on this, all the chromatographic nomenclature that was already defined must be used. If something is defined in chromatography, we belong to the chromatographic world, so we must use all the nomenclature defined in chromatography. And especially, IUPAC, International Union of Pure and Applied Chemistry, defined nomenclature for chromatography in this reference. 1993, E3, volume 65 of the journal Pure and Applied Chemistry, which is the journal of the International Union of Pure and Applied Chemistry. So this will be the reference for the naming. And Dr. Conway will pass you all the terms that were already defined, and we must use them. The problem is sometimes we have conflict, because countercurrent chromatography is also a liquid-liquid technique, 100% liquid, 100% liquid, with a variable stationary phase. All other chromatographic techniques, they have a constant stationary phase, so they don't need to define anything for the stationary phase, it's a constant. For us, it's a variable, and it's very important. So we have difference, and sometimes we have conflict. That's why I am talking on nomenclature with Walter today, because we have to decide, okay, when there is conflict, do we take that one coming from chromatography or that one coming from liquid-liquid system? And I will expose both because it's not solved yet. Okay, I'll go fast on those slides. You have seen this. First kind of countercurrent chromatographic column, hydrodynamic column. It's got two axes of rotation at least, sometimes more. Okay, I'll let you read this. I stay a little bit on those pictures because it's black and white in the manual, but that's you have seen this. Here I selected to put a machine with one column here, two columns there, and three columns. I think you cannot get more, because if you get more columns, the space in the circle, you cannot get a high beta, right? I think it's 3 columns is approximately maximum to get the acceptable beta. Okay, the next one are hydrostatic machine. We have not used experimentally on hydrostatic machine here. It's they work okay. They have one axis of rotation. They are called centrifugal partition chromatographs, CPC. This is a good naming for a hydrostatic machine. It could be a better naming for the technique itself, for CCC, but I doubt that we can supplant CCC. So the example of hydrostatic machines, you remember. You have seen this equation, but now I am using different letters, this showing that's not well standardized. What I will do fully with an example I prepared yesterday and a real example with molecules so we know what we are talking about. The retention volume of a compound depends on the volume of mobile phase in green and stationary phase in brown or different gray on your manual that you have in the machine. And that's it, nothing else. This is very important. It has nothing to do with nomenclature, but we have just partitioning that's responsible for retention of compound in the machine. That's why we can go from the small machine to the big machine. We don't have to worry. Maybe there is silanol interaction. No, we don't have silanol interaction in CCC. Maybe the pores are too big. Maybe the pore are too small. We have no pore in CCC. So there is difference. You see, this fact that we have only partitioning is a good point of CCC, allowing to go from small machine, like Jan Gerard will explain, to large machine and predicting everything. So now we have the distribution ratio to define. So I'll do it in a minute. First, let's go on this slide that you have. It doesn't show well when it doesn't show well on screen. Jan Gerard presented it in his talk, so you can, that's exactly the same. This slide shows what's written on the left. The stationary phase, it's a variable in countercurrent chromatography, and this is very different and unique from the other chromatographic techniques. In all other chromatographic techniques, you buy a column, gas or liquid, you open the box, and inside you have a chromatogram, and often they give you a little pot with the sample that they use to make the chromatogram. In gas chromatography, yes, often. I know Altec do it. I don't know if Agilent does it, but and the chromatograms say we have this compound, this compound, this compound, and we get this chromatogram. Please check it from time to time to see if the column is working okay. That's the way to test a column. You take the same sample, the same mobile phase, and the same column, and you should have the same chromatogram. Look at this figure. 4 chromatogram, and I could put more, but that's no need. Those 4 chromatogram are done with the same sample, the same column, the same liquid system, and you get 4 completely different chromatograms. Why? Because the stationary phase volume was, in that case, intentionally different. So this is very important. Or do I check if my column is working okay? I don't have to check it. It's always a new column. You are always working with a new column. You are preparing yourself. And this new column may not be the same as the one you have the day before because it's running a little bit faster, because it's different liquid system. You will have different SF, and you have to measure it each time. So this is not nomenclature, but that's, since we are at the end of the course, it's the point you should have in your head. The stationary phase in countercurrent chromatography is a variable, and we will need parameters to define this stationary phase. We don't need parameters to define stationary phase in other chromatographic techniques. So there will be differences. So now let's go in detail on distribution constant, page 11 on your printed text, and by chance you have page 12, which is very good. You have both of them on the same page. I have to switch from one to the other. Distribution constant and distribution ratio. what I will do to explain this, I'll go with an example. That's better. So I need my memory paper. So let's go with an example. We have a liquid system which must be biphasic. So I'll symbol this like this. So the liquid system I choose will be water and hexane. Okay? And I am working with benzoic acid. Benzoic acid, very simple molecule that I will write. Okay? Work with benzoic acid. Benzoic acid has an ionizable group and can go benzoate anion. So we have this reaction. That's a reversible reaction. And this reaction has a constant which is called Ka. Everybody agree on that? That's K. The log of this constant will be pK. Okay. What this constant is, it's the ratio of an equilibrium constant that you have in chemistry, this part on the numerator and that part on the denominator. So concentration of benzoate, concentration of proton over concentration of molecule in water. The little w is to say that's in water. The little w is useless. This does not occur in hexane, but I put it in anyway. Okay, on this, no problem. Then we put our benzoic acid in water, and we want it partitioned with the hexane. It does, and we have part of the benzoic acid going in hexane. And this has a distribution constant. And the distribution constant, which I wrote as D in this slide 11, is equal to the amount we have in the stationary phase divided by the amount in the mobile phase. In that case, will be the amount we have in hexane divided by the amount we have in water. So D, that I must write as benzoic acid, BH, it's the concentration of benzoic acid we have in hexane divided by the concentration of benzoic acid we have in water. And this is equal to 158. That's a constant. A constant doesn't change by definition of a constant. Okay? Now, this molecule can be ionized when pH change, and pH of water may change because carbonate gets in, it becomes more acidic, because you put something to increase the pH or something to decrease the pH, changing a little bit the pH of water. So you can form this molecule. But the problem is this molecule, it's an ion, excuse me, this ion, benzoate anion. This anion does not partition with hexane. So I still put a distribution constant of the anion, which I call B minus, and that's the concentration of the anion in hexane. divided by the concentration of anion in water. And since it's almost all in water, the literature value, you get a 0.005, which has not real meaning. It's practically nothing. That's also a distribution constant. But that's benzoate anion. It's not benzoic acid. It's different. It's another compound. Now we go to the slide 12. Partition coefficient, or this is distribution constant. Distribution ratio. The ratio of the total analytical concentration. So I need to have more room. See, I'm considering that I am mixing myself with my slide. This is what I define. Walter, you should tell me. It's all wrong.
Well, it's not exactly wrong, but much of it is not really relevant.
Yes. No, but if I stick to my slide, it's wrong.
Oh, yeah. Well,
You should tell me. Nobody is reading.
It's simple, like how. You never see that in chromatography. KD equals the one.
Yeah. The point I wanted to do is where is the constant and where is the variable. So this are constant when we have partition constant, distribution constant.
The one we call a distribution constant in chromatography is actually a variable. That's actually the intrinsic, or not intrinsic, that's the apparent partition coefficient in ionic equilibrium, which is not constant. It varies with pH. But we call it constant. But this other intrinsic constant in ionic equilibrium, we refer to what you've got written there as the intrinsic partition coefficient, which is for one species. And we use, at least I'm used to using the small delta for the abbreviation of that. It may vary depending on who's talking about it. But the KD is not particularly used in chromatography. KC is the standard, that's the IUPAC name, and they never use the D, because the D, the capital uppercase D, because that conflicts with diffusion coefficient,
That's conflict
for
with
which they
diffusion
do
coefficient,
use
yes.
the D, and which is relevant in our chromatography in particular. The diffusion constant is needed, and so the D and the K conflict. So anyway, the standard distribution coefficient in chromatography for many years now has been K sub C, and they usually drop the C because it's usually, the C means concentration ratio, but they usually just don't
So
use it.
what symbol would you propose for distribution ratio?
Officially, it's K sub C.
K sub C. That doesn't
uppercase.
fit with my slide. Okay, but
Yeah, but
let's
that's,
go for
I have,
K.
it's in my list of definitions there.
The point is, the distribution ratio is the total analytical concentration. That's the distribution constant, so that's the next one. So the D is wrong, but the total analytical concentration of a solute in the liquid phases. So
Right.
what do I have here? I have my ionization occurring here. So I also have COO minus when the pH is changing. But this I don't care. Just look at benzoate anion. So it means in the hexane phase, I have my acid. But in the aqueous phase, I can put hexane here. I have my acid, okay, plus the anion. And this is different. This is, I cannot say equal 100. It depends on the pH. If I change the pH, I'm changing this. So,
Let me make another point while you have that there. Well, what you say is true. The anion doesn't go into hexane, let's say. But if you used butyl alcohol, a measurable amount of anion would go in.
right.
But to come back to hexane, the benzoic acid, for instance, dimerizes in heptane.
Hexane
So
dimerase.
we have dimer there too.
I wanted to.
It
It's,
gets
it's
complicated.
already very complicated. So I wanted not to go.
Just the total, everything that has.
That's the point. You should realize that's really difficult point. So Walter is saying that in hexane, if you put more benzoic acid, you get a special dimerization which change even more. We still have this value for the distribution constant, 158. But the dimer has another value. So this value is not a constant. It's depend on pH. This depend on pH. And what I did, I calculate how it depend on pH, and you can, that's good, could be an exercise for student. It depend on pH. It's equal to the distribution constant. pH, I call it pH over 1 plus Ka over H plus. So you have a relation, mathematical relation between pH and distribution ratio. So if we look at this, if you go very acidic, very, very acidic, you get Kc, this become, if it's acidic, become big. So in a very acidic, you have practically 0 here, because it's become big. So Kc the two are equivalent, but in very basic, this is the opposite. In very basic solution, you have Kc is close to 0. Actually, would be, according to the literature, 0.05. I put close to 0. And in between, you get a sigmoidal change going from one to the other. And very often, pK of benzoic acid is around 4, I think.
Yeah, around
4, 4.5. It means that's the 4, 4.5. It's the pH where you have the most change between Kc, K, and D. That's where you have the raising part of the sigmoidal change. So you are pH 3. You have your peak eluting, very retained. You are pH 9. It's not retained at all in the same liquid system, different pH. So this is just the point I would like to make, why we have need to define clearly how we work with distribution ratio, distribution constant, because if it's a constant, you get your peak there and cannot change. If it's move with the pH, then you must take in account the pH of the solution and make calculation to guess where the peak will show up. So this occurs when you inject, and that's very often the case with natural product, when you inject compounds that are ionizable, that can change in the liquid system. If you inject toluene, heptane, dimethylbenzene, there is a lot of molecule. I think most of your essential oil molecules are not ionizable. Then no problem. I use distribution constant. I use partition coefficient. It's the same. because you don't have this equation not sensitive to pH. But there is a lot of compounds that have ionization capabilities, and you should know, is it the distribution constant or is this the distribution ratio? And they are different. But with one, this one is obtained by CCC. If you know the pH, you can calculate the other one, or vice versa. If you know one, you know the pH, you can calculate. So there is possibilities. More to add, Walter? So you say that's complicated. We would not like to...
It gets quite complicated, and chromatographers don't care. They only want the separation, and so we tend to call it...
And that's the point. The chromatographic don't care, but when they have a special division talking of ionizable compound, because they did notice also in liquid chromatography with solid stationary phase, if the pH is high, the compound moves. And you have peak reversal between the non-ionizable compound and the ionizable one, which move.
That's true
they know.
Here too in countercurrent. I mean, I worked out some systems where you could measure the pKa by changing the pH of the mobile phase. But chromatographers call this a distribution constant. Technically, it would be better to call it a ratio rather than a constant, because it's only constant for that particular system, providing you don't change anything for the chromatographic system. But if you change anything at all, it changes. And usually, you don't know what's in each phase. I mean, there are dimers, there are trimers, there are complexes between different compounds, and in the particular aqueous phase, the pH makes a great deal of difference. So you don't really know. You only know that if you don't change anything, it acts as a constant.
Yes.
Yeah.
Considering this value, 158 for benzoic acid, what Walter said, if you add propanol in here, this is no more true, because it's no more the same liquid system. But still, you have a constant for benzoic acid, which is no more this value. You should find it in the table.
Yeah.
Okay, we'll stop on that point and finish. I would like to finish showing how it's interesting to have a stationary phase. The first point is you can use the phase you want as the stationary phase. The other will be the mobile phase. The chromatographer, it's required to use silica as stationary phase and methanol water as mobile phase. You cannot use the other way. In countercurrent chromatography, we can use either one. So I remind you, depending on the one you use, you must enter the, right here. You must enter the mobile phase head to tail if you want the stationary phase to be the lighter phase, and the opposite, tail to head, if you want the stationary phase be the denser phase. And head to tail, it's also called descending, and tail to head ascending. For me, it's the same. Even if the liquid system is completely different, ascending is tail to head, and descending is head to tail. Yesterday, with natural sample of, I forgot your name, this lady, we did an extrusion. This method is very simple and very useful when you work with an unknown compound. So I just remind how it's easy to do. Step one, you do your classical CCC exactly as you were taught. And at the moment you say, is it all out? I don't know. You just pick up the line and put it in the other phase. Step two, to do this, you must not change anything else. Don't stop anything, flow or rotation. You just, if there is a bubble, it's even better. You see the bubble, you can see where you're changing. If you have two pumps, you are rich like in Gévaudan, okay. You can put two pumps, two lines. But I do it with one pump, one line, and it works pretty well. Step two, instead of pumping the correct phase, you'd pump the other phase. So you are not respecting the rule that exposed here. The consequences is your phase is pushing everything which is in the colloid, maintaining the separation that you started, and you get your separated peak in the stationary phase coming out. And after one column volume, just one column volume, you are sure everything that was injected is in the tubes. So that's, and the machine is ready to start over. So Guy Harris from Merck told me, I am using this daily, it works so well. He was very happy. Unfortunately, he lost his job, so it's not related. So elution of all solute, and when you are finished, you have, okay, the position of the peak, you can even relate them to their distribution constant if you have a continuous detector. If you analyze in each tubes, it may be more difficult. So this is published. You have the reference down here. And this, we got commercial advertisement before, so I skip it. And this also, you got information on this reference that are connected to special issue in the CCC conference. So these are all special issue: Beijing, London, Tokyo, Washington, and the last one this year was with Rio. Okay, this was the team, IUPAC team, that prepared this report. So you have these smiling guys called Jan Sutherland. You know this guy. This is Tatiana Mayutina. This is Oleg from Russia. Jan Sutherland is from Brunel University. I'm from Lyon. Tatiana Mayutina, Oleg Shpigun, and Boris Spivakov. So we had a big Russian hand on the committee. All three from Moscow. Vernadsky Institute, let me read it. Vernadsky Institute of Geochemistry, Russian Academy of Science, Moscow. Now we are starting a new team to work on nomenclature, and will be less Russian. Now I will put some slide from Walter.
One point I like to make, that countercurrent chromatography is not readily accepted as a chromatographic technique by many well-known chromatographers. They consider it not too useful for very many things, and they feel it doesn't meet the IUPAC definition, and so they don't give it much consideration. On the other hand, people who find it useful don't agree with that. Now, and it clearly is chromatography to those who use it. Now, the IUPAC definition you have on this slide and in your book, and this is a direct quote of the IUPAC definition, that chromatography is a physical method of separation in which the components to be separated are distributed between two phases, one of which is stationary, the stationary phase, while the other, the mobile phase, moves in a definite direction. The conflict with whether it is or isn't chromatography comes in those last few words, moves in a definite direction. Now, the way, and they do have, I counted at least 22 examples of types of chromatography, one of which includes partition chromatography, but they mean liquid-liquid partition chromatography where one of the phases is immobilized on a stationary matrix, like diatomaceous earth. This was widely used back in the 50s and 1950s and even earlier, where you would immobilize one phase, say water, on a diatomaceous earth or some other kind of phase, cellulose sometimes, and then you would pass an organic solvent over it, and you'd get partition between the two phases if you ignore any adsorption that inadvertently occurs onto the matrix. And so you did have liquid-liquid partition chromatography. The problem was that it was difficult to keep that stationary phase there, and you couldn't put very much on there. You could only put a small amount, and you would tend to wash it off as the other phase went through. But nevertheless, it worked, and in many cases, adsorption was not too great a problem. And there are many papers that are published on separations using that method. Now, the problem, I said, is that it moves in a definite direction, is the conflict, because they're saying one phase is stationary and fixed, and the other one moves in a definite direction, either one way or the other way, but not both. So that's where the conflict comes. Now, in much of the counter-current, what we call counter-current chromatography, we do actually have exactly that. You put a stationary phase in the column. You don't have a matrix, but that's not really critical. And you do pass the liquid through in one direction. And that would meet their definition. Where you start putting it in one direction, well, even if you went in one direction and then stopped and floated out the other direction, that's done in solid phase chromatography too. So that would meet it. It really comes when you put two phases in, and the name already turns them off, because it implies that you do have both phases flowing. And while Ito did have both phases flowing in his very initial work, it later evolved that the one phase moving became rather common. Now we're into all kinds of situations where you can manipulate both phases in various ways. And I still think it's better in most cases to consider it chromatography rather than start splitting things into chromatography procedures and extraction procedures, because then we'll get even more conflicts. And usually the same mathematics to explain it does apply to both. It's just that you have to modify it a little bit when you go one direction or the other. Now, okay, here's some of the problems, the historical problems with nomenclature. The names that were assigned as the instruments kept being developed don't reflect the structural relationships between the instruments. Nothing much can be done about that, and by the time it became necessary to set up some kind of notation that did relate the names to the instruments were somewhat forgotten or not. It wasn't so relevant. It's only relevant if you want to actually see why some work better than others. Another criticism, though, is that many of the methods that the applications for counter-current chromatography that have been published, they do not cite the chromatographic literature from which they were derived. Like I said, many things were done back in the 50s with liquid chromatography, but on a matrix. Many of the things that then began to be developed in counter-current chromatography were exactly the same, sometimes almost direct copies, but they don't cite the earlier work. Well, that's not fair to the chromatographers who did that earlier work. The earlier work was quite valid, and while there may be advantages to do it in a counter-current apparatus, you could use a larger sample and so on. The liquid was perhaps more stable, but this is not fair to the chromatographic community, and so I think it's good when you do something to go back, if at all possible, and find out who did that before, or if you're copying from something that was done by another type of chromatography, cite it. That makes this then a part of the chromatographic field. Uh, I mentioned there in retrospect, the centrifugal partition chromatography might have been a better generic name for the entire technique if that had been introduced earlier instead of countercurrent chromatography, because the countercurrent aspect could then have been slipped in later, but putting it in at the beginning turned off a lot of chromatographers. So I think to recommend what to do, always speak and write as a chromatographer. Don't put countercurrent chromatography as something special and different and better and unique. It may be those things, but if you want to keep it in the field of chromatography and you want chromatographers to adopt it, then you have to be one of that group. Now, another important thing is always use chromatographic nomenclature and symbols, and where possible, relate the countercurrent theory to chromatographic theory, or if they differ, contrast them, but they don't really differ that much. Now, what I've done on the next several pages, I'm not going to go through them one at a time. There are two sources of chromatographic nomenclature, two main sources. One is the IUPAC booklets, and I cited at least one of that reference on the first slide. Those are all available now on the internet. One problem is it's rather difficult to use them. They used to publish these things in books, and they had what was called an Orange Book. And the Orange Book came out, I think, at least 4 editions, and they started publishing these back in the 1930s. Not just for chromatography, they name everything in physical chemistry and electrochemistry and everything else. They decide on what people should do. I don't think many people read them. The books they were never very common. I happen to have 3 or 4 of the older Orange Books. It is easier, and then they occasionally publish it in the IUPAC, what do they call it, the Journal of Pure and Applied Chemistry. But there again, very few people read it, and so they do publish it. And another good thing about it is they do not retain copyright on these things, so anyone is free to quote it anywhere, and that's a good thing. But now it's all on the internet, and you can find it on the internet. And if you're looking for a particular thing and you know the internet address that they give it, you can find it, or you can go to their website and you can try to find it. But you have to know what to call it or something. It's not like reading the book where you can thumb through and find what you want, get general information. So that complicates matters. But most of you are probably familiar with the LCGC publication, which is a free publication, but which is a rather good one and is widely read by chromatographers. Most chromatographers, I think, get the LCGC magazine. Now, they published in 2001, they did earlier too, but they updated it in 2001 and published a list of chromatography symbols and definitions. And I think there are about 200 or more symbols and definitions in that list. I have a copy of that particular publication. And what I did here on these pages, I went through the publication and picked out those terms which are at all relevant to countercurrent chromatography, and then there are fewer than half of the terms are relevant. So there may be about 80 terms that I simply copied here. I just photocopied them onto these pages, and these are relevant to countercurrent. Now, these reflect the IUPAC names. They say that in the publication, and Etret is a famous chromatographer who was mostly responsible, I think, for making up, at least for publicizing, most of this information. And he's involved with that 1939 publication that was cited. But he's still with us, and he's still writing. Anyway, I listed these things on here that I think are relevant. Some you find are not, some are more relevant than others, but it cuts down the list. And they're listed alphabetically. And so I would just point out a few of them. And let's see, if I go to that page 4, down in the lower left corner there on page 4, you have the distribution constant or coefficient, and the official symbol that is for my UPAC and the LCGC summary is K sub C for that, and they show there the way that you would write the equation. Retention time is equal to mobile phase volume plus K sub C times V sub S. Now the C implies that you have concentration in both phases. And usually in most chromatographic publications, they don't use the C. They just use the uppercase K. But if it's not in concentration, then, for instance, they give an example here. If the solid stationary phase, in the solid stationary phase, K sub G can be used, meaning that you have a weight concentration. But in countercurrent, in fact, it almost always is concentration in both phases. Yeah.
Just a question.
Yeah.
It's not a constant.
No, it's not. But that doesn't matter. That's why I think maybe it is better to call it a ratio. Call it a distribution ratio rather than a constant, but they refer to it as a constant.
They refer to this as a constant, and it's a ratio,
Right.
a constant.
It's really a ratio. It's constant in a particular system. If you don't change anything in the system, and especially they don't have too much opportunity, although in, let's say, reverse phase system, reverse phase on C18 silica. If you're running a phase where you change the pH, this will not be constant. If you change the pH, that will change. But if you keep the pH the same, it's a constant. So they call it a constant in the sense that it is constant as for a particular chromatographic system. If you change that system at all, if you change the temperature, if you change particularly the pH or the solvent system, that will change. So, for instance, in a gradient system, that changes. It continually changes. But they do call it a constant. There was really nothing wrong with the term partition coefficient that's been used, and I'm not sure that it doesn't still exist for people. Well, for people in physical chemistry, I think they still may use partition coefficient. And in partition chromatography with a stationary matrix, maybe they still use it too. But I don't know. For every so many years, some committee decides that everyone should call it something different, and that's what happens. But it's not always best choice that could be made. So you do have to realize that is not a constant. It's what I would call the apparent partition coefficient, or the apparent distribution constant. It varies with certain variables, but it's constant within certain terms. But nevertheless, that's the nomenclature that they use. But a ratio, okay, then if it's a concentration ratio, that's not saying that it's constant. Either one, I think, would be acceptable. Maybe ratio is a better term, or coefficient, either of those. But they want to use distribution instead of partition. Now, the important thing there is that the K sub C is always the ratio of concentration in stationary phase over mobile. That's always true. Stationary phase over mobile. So if you switch phases, then your constant would become reciprocal of the other. And the ratio is determined as the total amount, whatever form it's in, whether it's a dimer, an ion, an intact species, the sum of all those in one phase divided by the sum of all those in the other phase. So that's the way it's defined. And they never do use D, uppercase D, because that conflicts with another term, and that's the diffusion coefficient. For the diffusion coefficient, they do use D, and so they don't want those terms to conflict. Okay. The 11. Yeah, here, 11, we have there, now they do say partition coefficient K, and then they, I get it on my, yeah, partition coefficient K, the ratio of equilibrium concentration of solute stationary relative to mobile phase, also called the distribution coefficient, and there they do have the symbol K sub D. But I made the note that that is not commonly used. The distribution constant, K sub C, that's the official symbol for it. But the K sub D is not so bad. The uppercase D presents a problem. Let's see here. Yeah, okay, on the upper left there, the phase ratio, beta. Beta, they use beta to mean the phase volume ratio, again, stationary over mobile, stationary phase volume over mobile, they call beta. So we need to make a little distinction there because we have two betas. The beta, one of the betas is the ratio of the distance from the planet axis to the particular distance, particular coil that you're talking about, distance from the center of the axis, divided by the orbital radius. And so that came from the beginning of Ito's work. So it's convenient for us to call that beta sub r for the radius ratio, and then we need beta sub v for the volume ratio. So it's not a big deal. That's a bit of a conflict even within our own field. Okay. And then on page 13, what do we have there? Yeah, they use a KD again there in the retention volume. Yeah, on the lower right in the retention volume, they write the same equation that was given before, but there they're using a KD. So, but as I say, KD is not commonly used. Usually the plain K is used. And but that doesn't present too much of a conflict anyway. But there is some conflict even within the chromatographic community as to what these symbols, and between them and IUPAC. Problem with IUPAC is they're a very, very bureaucratic organization. They take forever to get things going through. They go through a committee, and then another committee approves it, and then eventually they say it's official. But that could take 10 years. It's not a rapid process. You can see this if you look through their older literature. And they have committees for different groups, like there's another committee for physical chemistry. And they have another committee for extraction, a completely separate group. They don't seem to pay attention to one another. So there doesn't seem to be enough effort to keep symbols consistent across the whole range of chemistry. There isn't any need to have these conflicts. There's no reason they can't all use the same symbols. I mean, I taught undergraduate students and graduate students for 33 years, and these kinds of conflicts are confusing to a student. It makes the equations look different when they're identical. And so, I mean, if you have two different definitions in making up an equation, you'll think it's a completely different equation, and it's the same thing. So, okay, that's really about all I wanted to say about this. At the end, I made a note on the bottom indicating I didn't write that those definitions or anything. That's just a summary of what exists, and you can get this. It's updated more or less continuously on the website for the LCGC. I gave that symbol, that address on the first page there, so you can look it up and see what it is. It's easier to find in the printed publication rather than the website. But I gave you the shorter list here, so you can consult it if you're concerned about what nomenclature to use. And as Alan has pointed out, we do have a committee that is discussing these things, and nothing is final at this point. You can see that even within our committee there's discussion about what's the right way to say these things.
I would like to add one word.
Yeah.
Walter, you did the best slide I've ever seen in here.
Oh,
You're
yes.
skipping it.
Yeah.
This slide is wonderful. Look at the LC columns. You see retention time, volume, retention factor, conversion on the left, liquid chromatography. Look on the right, that's CCC.
Yeah.
What's the difference?
Yeah.
No stationary phase volume on the left. Never,
Right.
never. They don't care about the stationary phase, and it's critical for us, and we see it clearly there. On the left, you have MMM, which is mobile phase. Where's the stationary phase? We don't care. It's a constant, and they even don't know the volume of the stationary phase. And we do. And we have VS, VS, VS everywhere on the right column. So this slide shows very well the big difference we have. It shows also that what you want to show, that it's the same family. So we have agreement, and we must work with them. And we are not competitors at all, but we should accept each other.
Yeah, I think we have to accept what is common practice and not start arguments over it, and not make ourselves sound as a different community. You can see these equations for LC. Usually they're presented in values of time. These are in values of volume, but they are identical equations. These equations are identical, even the ones that are here in terms of capacity ratio, or now they call it retention factor. Even these two equations, they are equivalent. If you use the right equivalency down here, you can convert one to the other. The other thing about it is, with the countercurrent chromatography, you can look at this and you can see already, just by looking at the chromogram, what the partition coefficients are before you do any calculations. Can't do that with liquid chromatography. It comes down to the fact you don't know the stationary phase, and so the chromatogram looks different. When I was teaching chromatography to undergraduates, I found we went through, I taught in School of Pharmacy, so we taught a lot of ionic equilibrium first. That came ionic equilibrium and extraction chromatography. But once you go to countercurrent chromatography, now it's very easy to go backwards into solid phase chromatography. Then and you can see then what the difference is. Here we're really getting a plot of partition coefficients, or of stationary phase volumes, whereas
this is a kind of arbitrary factor. This is the quantity in both phases, whereas this is the concentration in both phases. And while they're related, this one is visibly apparent, whereas that one is not. You end up getting repetition of the mobile phase volume. So it's much easier to teach countercurrent chromatography first, but you have to get a countercurrent chromatograph into all the chemistry departments, you see, in order for that to ever happen. And very few have one. Okay, I will quit.